Here's a ball on the ground. When I throw this ball upwards, there is an acceleration while that ball is in contact with my hand that is unknown. Okay? I'm pushing on the ball. We don't know what the acceleration is because there's a couple of forces acting on that ball. There's the force of my hand pushing on it, and there's the force of gravity pulling it down. But as soon as I let go of the ball is going to continue to move upwards. Can you tell me what the acceleration of the ball is once I let go? What is it always going to be once I let go? Good, negative 9.81. While it's in contact with my hand, all bets are off. This is not a straightforward question when it's in contact with my hand. We don't have to know how to deal with that, at least yet, when it's in contact with my hand. But as soon as gravity is the only thing influencing it, once it leaves my hand, then we know when it's going upwards that the acceleration is negative 9.81. Can you explain to me why it's negative even when it's moving upwards? Bart? Good. When it's slowing down in the positive direction, that means it's got to be a negative acceleration. At some point, it's going to reach a maximum height, right? We know this. Intuitively, we know that a ball that goes up is going to come back down. Can you tell me what the speed of that ball is when it reaches its max height? Just before it comes back down, Carrie? 0. Good. The speed of it is 0 when it reaches its max height. Can you tell me what the acceleration of that ball is when it reaches its max height? There's a tough question. Zach? Good. Excellent. Negative 9.81 meters per second squared. Just because it's not moving doesn't mean it's not accelerating. The velocity is 0 for a very, very brief time, for an instant in time. It is changing velocity, though, at all times. It is slowing down, slowing down, slowing down as it gets closer to the top. It is stopping, and then just as quickly as it was slowing down, it starts going back down in the negative direction. The acceleration continues to be negative 9.81. Carrie? No. No. Now the ball is going back down. What's the acceleration of the ball as it falls back down toward the ground? What? Good. Negative 9.81 meters per second squared. When it hits the ground, all bets are off. Okay? It is moving as it hits the ground, not after it hits the ground, but as it hits the ground, it's moving. Okay? But while it's in contact with the ground, again, we no longer have just the influence of gravity. We've got some other influence as well. So we don't know what the acceleration would be in that case. We don't right now know how to figure that out. Okay, does that make sense? The acceleration from the time it leaves your hand is neg 9.81 till the time it comes back down and hits the ground. Its velocity changes. It is going fast here. It slows down. It stops. It speeds up and goes fast again. The velocity changes, but the acceleration remains 9.81 meters per second squared. Here's a position versus time graph. Position versus time graph. Let's call it vertical position. Okay, let's go say it goes straight up and then straight down. I've drawn it kind of parabolic here, almost, just so that you can kind of see the up and the down path. But let's assume that it's going straight up and straight down. Let's plot a graph of the vertical position versus time. What do you think that graph would look like? The vertical position versus time. It would look like this. Okay, the vertical position is increasing, is increasing, is increasing, but the rate at which it increases is decreasing. Right? In other words, look, we learned that that's slowing down, right? The ball, as it goes up, is slowing down. Then it reaches a peak height, and then it comes back down in the other direction. That would actually be a speeding up in the negative direction. Vertical position versus time. What about vertical velocity versus time? You haven't done velocity time graphs yet, so this one might be a little bit tougher for you, but just out of curiosity what it would look like here. Sorry, no, sorry. Meant not to plot. That's not the question I wanted to ask you, actually. Okay. Yes, it is. Sorry. Confusing myself here, Lewis. What about you guys? Sorry, what did you say? Would it just be the opposite? Well, the velocity is decreasing, yeah. Velocity is decreasing, 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 decreasing until it reaches 0 when it reaches the peak height, right? And then it increases, 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 increases. Right? Does that make sense? So it is just the opposite. Good. Yeah. Let's make it velocity. Oh, yeah, you know what? Yeah, no, that's wrong. That's wrong. Yeah. Boy, am I ever confusing myself. No, you're absolutely right. That's wrong. Velocity versus time. The velocity is changing, but the rate at which the velocity isn't changing. So it actually looks like this. The velocity is decreasing, 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 decreasing. It's 0, and then what happens? It increases again, but in the negative direction. Is that what you were saying? Yeah, and you're right. Make sense? If it doesn't make complete sense right now, don't panic about that. A, because I was a little bit confusing in the way that I showed you. I got confused myself there for a second. And B, we'll talk more about velocity time graphs a little bit later on. All right. Let's do a question. A clown. Hey, this is going to be a fun day in physics today. We're talking about clowns. I should have dressed up as a clown today. A clown throws a ball upward at 10 meters per second. What's the maximum height the ball reaches above its launch height? And what's the time that it takes to do so? So this is kind of what we were just talking about, right? It's almost the same thing as we were just talking about, except this time we have the context of the clown throwing the ball. Let's identify whether this is group A or group B before we look at even any givens here. This ball will accelerate or decelerate, as the case may be, right? So it's got to be a group B problem. Let's write down some givens now. Something is 10 meters per second. Can you tell me what that is? The clown throws the ball upward at 10 meters per second. It's a velocity, right? Is it V? Is it VI? Is it VF? What is it? Good, VI. The instant it leaves the clown's hand, this is how fast it's moving, 10 meters per second. What else do we have if we read between the lines? Yep. Okay, if you're analyzing the trip up, just the trip up, forget about the trip down. If you're analyzing just the trip up, VF would be 0. Remember we said when we were reviewing there, as it goes up, it slows down, it slows down, it slows down. When it reaches its peak height, it stops. So VF would be 0 if we're analyzing just the trip up. There is one more thing that we have if we read between the lines. Don't even really have to read between the lines. It's the same for a lot of these questions. Yep. Right. And it's negative 9.81 meters per second squared because it's a downward acceleration. Even though the object is moving upwards, it's a downward acceleration because it's slowing down. Okay, we want to find the max height. What variable is it that we're going to solve for to find the max height? Yep. Good. Let's find the displacement when VF is equal to 0. And then we want to find the time as well. Now, you get a situation like this on a quiz or a test where you're asked to solve for two things. Generally, you're probably going to solve A first and then do B. But is there anything wrong with solving for B and then using that number to go back and solve for A? Of course not. Of course not. Do it whatever way you want. Okay, there's always more than one way to do the question. And if your way allows you to do B before A, that's fine. Doesn't make any difference. What am I going to do here? Let's say for question A, we use VF squared is equal to VI squared plus 2AD. That seems to fit, right? Solving for D here. Let's go through that process of rearranging again, those steps. What's the first step in rearranging this, Jordan? Get it on top. Is it on top? Good. What's step 2, Leah? Good. Get rid of what's not attached. Leah, is there anything that's not attached? VI. Good. So how do we get rid of VI? Good. Take it to the other side by subtracting. VF squared minus VI squared. By the way, you can take the squared over with it, right? You don't have to just take VI over. VF squared minus VI squared is equal to 2AD. Step 3. Step 3 was what, Tyler? Get rid of what is attached, right? And what is attached to delta D here? 2 in the A. How are we going to take that over? Good. Remember here, when you divide that, whoops, that should be a minus. When you divide that, though, you're dividing the entire left side by 2A, not just one of those variables. That's equal to delta D there. All right, good. So delta D becomes VF 0 squared minus 10 squared over 2 times neg 9.81. So it becomes negative 100 over negative 19.62. I think it works out to be 5 point, is it around 5.1? 5.01? We're actually going to need 3 digits here because of, this was 4 digits, right? This was 3 digits. Final answer should have 3 digits. 5.096, so 5.10 then I guess it would be, right? Yeah. We're not panicking about significant figures right now. If you didn't understand that whole thing with significant figures, that's okay. But we still want to use the correct number, whether we're focusing on that or not. So a little bit harder than the last set of questions you did with gravity. Yeah, I think so. Okay, you had to recognize here that VF was equal to 0. You guys did a good job at that, as you always do when you have to read between the lines. Okay, don't overlook little things like that. You're going to be good with all these questions if you don't. Solve for B now. How are you going to find that time? Good thing I caught that mistake myself, to not overlook that. Yeah. A equals delta V over delta T. It's certainly valid. We've got A. We have VF. We have VI. Looking for T. Why not? It fits. It's valid. Why not? We're solving for T, though. What's the first step in rearranging this one? It's a short equation, but ironically, it's sometimes a little bit harder to rearrange because we're solving for T. What's the first step? Get T to the top. It's on the bottom. How do I get it to the top? Right. It's already divided, so I'm going to multiply it, right? A times T equals delta V. Now I want to get T by itself. A is attached to it, so I'm going to get rid of the A by dividing. Little shortcut there. Little shortcut is when you got something like this and you want to switch places here, the A and the T, just switch places. Okay, when one's on the top and one's on the bottom, you can do that. You can switch places like that. All right, delta V. Delta V, 0 minus 10 over negative 9.81. So that's going to give me a time of, I don't know, 1.01. I'm guessing. 1.02 seconds. All right. Now we can have a look at the one question that goes along with it. This is great, eh? We just had a clown question to brighten our day up a little bit, and now we get our practice problems, and it's not even practice problems. It's practice problem. Even better. All whilst you still have this image of this clown making you happy in your heads. Okay, let's see what you can do with this one question, okay? Let's look at this one now. It says the slingshot drops riders 27 meters from rest before slowing them down to a stop. How fast are they moving before they start slowing down? All right, this question, if I'm a 16-year-old student going through physics for the first time, this question confuses me a little bit, the wording of it. It drops them 27 meters. How fast are they moving before they start slowing down? So you're being dropped down, okay? Here's the ball, here's the rider, whatever, being dropped down. It speeds up, it speeds up, it speeds up, and then obviously you want to slow them down gradually before they hit the ground. So this is the point of free fall, or the stage of free fall, and then this is the stage of slowing down. This is the stage that we want to look at here. Okay? We want to know how fast they're moving right here. How fast are they moving just before they begin to slow down? In other words, we want to know how fast they're moving after they finish free falling. All right? So what do we have here? We have that the acceleration during that free fall is -9.81. What's the acceleration right here when they begin to slow down? What's the acceleration in this stage, Bart? Right. Not with anything that we know right now, at least it can't be determined. We don't know what that acceleration is. We do know which direction it is, though. If you're slowing down in the negative direction, the acceleration would actually be upwards. It would be a positive value, right? If speeding up in negative direction is negative, then slowing down in the negative direction would be positive. All right, we're looking at the acceleration phase here, though, the free fall phase, where A is -9.81. What else do we got here? Something's 27 meters, right? 27 meters. What's that? Aiden? Good. The displacement. Is that right? Displacement is 27 meters? Yes, it should be negative because it's downwards, right? Okay. So Aiden, you're right. You answered my question correctly. It's the displacement. I just didn't give you the right question. It should be negative 27 meters. Anything else reading between the lines here? Anything else, Lewis? All right. It starts at rest. Again, this is what your skills are, right, guys? You guys are really good at spotting those read between the lines things. Yeah. No, the final velocity isn't 0. Okay, remember, we're looking at this trip right here, the free fall. It starts at 0. It speeds up, it speeds up, it speeds up, it speeds up. It doesn't stop right here. It's not 0 meters per second right here. It's moving at a certain speed pretty fast, and then it begins to slow down. Down here, v would be equal to 0, but I'm not analyzing the trip where it's slowing down. Okay, Bart said just a few minutes ago, we don't know what that acceleration is. We have to analyze just the free fall stage. Okay, what's the velocity right there? We don't know what that is. In fact, that's what we're trying to find, right? How fast are they moving when they begin to slow down? What's VF for the free fall? Not VF down here at the end of the slowing down, but VF at the end of the free fall. All right, I think we're going to use that VF squared one again. Equals VI squared plus 2AD. That disappears because it's 0. Square root of 2 times negative 9.81 times negative 27. And I assume that gives me the answer that's in the book of 23. Is that right? So a little bit different than the example that we did, but still one of those ones that's a little bit more of a step up than some of the other questions that we've done. Okay? Read between the lines. Understand exactly what's going on. Okay? Understand that this is really two problems. There's the free fall portion, and then there's the slowing down portion. But we only know anything about the free fall portion. So you need to ignore, as Bart said, that last portion. I got one more example with you on this stuff. This one's on page 60. I'm going to give you a chance for 30 seconds or so just to read this, not to do it, but just to read it and see if you can come up with any kind of ideas, like, you know, the reading between the lines, the predicting, and so on. All right, let's take a look now. Here we are with the clown again. It's clown day at HTA. Clown throws a ball upward at 10 meters per second. Find the time that it takes the ball to return to the clown's hand from the maximum height. So the ball goes up, ball goes down. How long does it take to go up and down? Up to the maximum height and then back down. And then what's the ball's final velocity? What do we got here? What do we got? Initial velocity of 10. Is that right? A is neg 9.81. Yep. Oh, okay. So you're saying yeah, it's just saying to the cloud sand from the maximum height, isn't it? Yeah. Yeah, that's a good point, actually. Yeah, that question is only actually asking us to analyze the trip down, right? Yep. There's a couple ways of looking at it, actually, and you're both right, actually, both of you. Let's do it Stephanie's way here first, okay? If we're analyzing just the trip up, okay, just the trip up, we can say that VI is 10, and VF there would be what, Stephanie? Right. Find the time. A is equal to delta V over delta T. Delta T ends up being equal to delta V over A. 0 minus 10 over neg 9.81, 1.02 seconds. So it takes 1.02 seconds for the ball to go up. How long do you think it's going to take for the ball to go down? Listen, if the ball travels a certain distance up and it slows down at 9.81 and it takes 1.02 seconds, and it travels the same distance down and it accelerates at 9.81 down, it's going to take how long? Same thing, right? Same thing. This is the time that it takes the ball to go up and stop, but it's also the time that it takes the ball to start from rest and go down to the bottom. Yeah, VF would be equal to 10 meters per second as well, 10.00 meters per second as well. Now, the way that you were suggesting, Lewis, you were essentially saying, I think, that do in reverse, basically, right? You would have said VI, if you're analyzing the trip down, VI would be 0, and VF would be 10, right? And then you'd go, you would use the same equation probably and solve for T that way. That make sense? So both of you are right. Just depends on how you want to think of the question. I'll give you a chance to write that down, and we'll show you the next one. All right. So you can do this one, okay? All right, if we're all okay with that question, we'll just move on here and assign this homework here, page 63, number 2 to 16. We're not going to work on that right now, but we're going to assign that, and if we have some time later on in class, then you can work on it then.